My name is Charlie Brewster, and I'm presenting you today my research on the magnetic properties of carbon-sulfur composites under a hydrogen atmosphere. But before I get started, there we go. Before I get started, I have to go that way. Before I get started, I need to address a few questions you might have. One, why study the magnetic properties of materials in the first place? And that's because in the recent few decades, it's become very apparent that we need to develop new materials to help facilitate technology such as quantum computing, spintronics, and even magnetic gas sensing. We also need to understand how external factors can influence these properties in order to develop new applications for these. So it's our hope that by understanding how these materials interact with the hydrogen atmosphere, we might be able to develop new technologies to help support the growing hydrogen energy economy. The next question you might have is why look at sulfur-carbon composites in the first place? And magnetically, these are actually very interesting materials. Previous reports have shown the presence of superconductivity, ferromagnetism, or even spin glass, sometimes existing concurrently within the same material. We've also previously shown that these materials are beneficial for hydrogen storage, producing greater densities of hydrogen at milder pressures. So the particular sample I'm going to be talking to you today is a carbon nanotube encapsulating a polymeric chain of sulfur. We've confirmed the presence of this polymeric chain through Raman spectroscopy and X-ray photoelectron spectroscopy. Using XPS, we can also get a composition of our material, and we can see there's about 15% weight of sulfur inside our composite. As for the metal content of our materials, we've also done a few bits of characterization, looking at optical emission spectroscopy. And what we're paying particular close attention here is the ferromagnetic impurities, something like iron, nickel, or cobalt. And what we can see is some residual catalyst left over from the manufacturing. As for the magnetic results of these materials, well, we can actually see that there's a ferromagnetic response, a superparamagnetic response in this material, shown by that sigmoidal curve at high temperatures. This is something that's characteristic of ferromagnetic materials. So we can see here isolated pockets of cobalt within our sample. This isn't too bad, even though it's an impurity. Now we know it's there, we can model it, and we can subtract away that superposition and be left with what is just our carbon and sulfur and see a diamagnetic response inside this. But how does hydrogen change these properties? And this is actually something that's really interesting. If we look at the interactions with hydrogen, we can see this increase in the paramagnetism. Why is this? If we subtract one from the other, we can actually see at low temperatures it is pretty much purely paramagnetic, and is limited only to the low temperature results. This is unusual because hydrogen has no unpaired electrons. You'd expect it to be a diamagnet rather than a paramagnet. So something clearly is happening in the system that is rather unexpected. If we look at the magnetization versus temperature data, we can get a little bit of an insight into what's happening. And if we start down at the bottom there, down at 2 Kelvin, and warming up, we can go through various phase changes of hydrogen, which we can detect using squid magnetometry. As we go through the gaseous phase, we start to desorb from the surface. But upon cooling it back down with an applied field, we end up with a different pathway as we come back down. And as we get down to that solid stage, that really low temperatures below 10 Kelvin, what we see is this inflection up into a paramagnetic state, which again was quite unexpected, showing some sort of interaction is occurring in our sample. So in conclusion, the magnetic response of our sulfur-carbon composites is largely dominated by a ferromagnetic impurity. We can model it and subtract it. We also shown that these properties can be altered by the interactions with hydrogen, giving us a stronger paramagnetic response. We've also shown that squid magnetometry can be used to observe phase changes of hydrogen within our sample, which again, quite interesting, gives us a few ideas for some use cases. As for future work, I'd love to do some more experiments with materials that have fewer ferromagnetic impurities to try and identify what is the hydrogen interacting with. And lastly, a few other experiments I'd like to conduct is different hydrogen pressures and temperatures to maybe get a calibration curve set up to see if we can identify how much hydrogen is in our system using magnetometry. I'd like to thank my collaborators and the BCI technical support team for their endless support. Thank you. If you have any questions, I'll take them now, or please come find me at my poster. Thank you.